Howdy and welcome back. So here's the topic I guess we've all been waiting for, dynamically allocated objects. Before we get into this, I just want to go ahead and point out that we are going to be responsible for the lifetime of these objects. It'll be our responsibility to request their creation when we need them and also return the memory allocated for them when we are through with them. So let's go ahead and, I guess, begin. So we can dynamically allocate memory on the free store in C++ with the new operator. So anytime we're saying new, we're thinking something's going to be allocated on the free store and that we're going to control the lifetime of that object, which means we'll need to call delete on its address when we are through with it. So the new operator is going to allocate memory for an object or an array of objects of a specified type on the free store. The new operator is going to return the base address of the region of memory allocated for that object or an array of objects. So if we wanted a new integer object on the free store, we would request that by writing new int. If we wanted an allocation of, say, some contiguous number of integer objects on the free store, so say an array of 10 elements, we would request that by saying new int and then using subscript notation to denote the capacity of that array, so the total number of integer objects available to it. Now notice that in both cases, an address is going to be returned. Well, where do we store that address? The only type of object that we're familiar with up to this point that stores addresses is going to be an object of the pointer type. So in this case, free store object is going to be a variable. It is a named object residing on the stack that is going to store the address of our new integer object. So new returns an address. That address gets stored in free store object. Likewise, if we're requesting a new array, an array on the free store, that new operator is going to return an address, and we could go ahead and store the address to our dynamically allocated array in free store array, which would be a pointer to an integer object residing on the stack. So notice in both cases, we have a variable or a named object that is going to store the address of our dynamically allocated object. Okay, remember that if we were to see out free store object or free store array at this point, what would be printed to standard output would be the address to those objects respectively. Now, we can go ahead and interact with, say, our new integer object by just dereferencing that variable. So if we wanted to assign, say, the value of 11 to the free store object pointed to by free store object, we'd go ahead and dereference that address, interpret it as an integer, and we could go ahead and put in the value of 11 into it. If we wanted to access, say, the 0th index of our free store array and assign it the value of 7, we could go ahead and use subscripting to do that. So in both cases, we're indirectly accessing these free store objects through pointers. So to get to them, we essentially dereference their address, which is stored in one of these pointer objects, which would get us to that object residing in the free store. Now, when we're done interacting with these objects, when we no longer need them, it is going to be our responsibility to explicitly deallocate the memory, that memory when we are through. We do this by using the address as an operand to the delete operator. So notice here, we're calling delete on the address, so the value of free store object. Remember, if we were to stdc out free store object, what would be printed to the screen? An address. So you can view this as delete followed by the value stored in free store object, which is an address. So you're calling delete on the address stored within free store object. We are not deleting the pointer. That is something that a lot of students will say. Instead, we're simply passing to the delete operator the value stored in free store object, which is the address of that dynamically allocated object for which we'd like to return its memory. Now, calling delete to deallocate memory for an array is going to be very similar, but there's a special delete operator for arrays. And it's just going to be delete followed by empty subscript, and then the address of the array that we'd like to have its memory deallocated for. So in this case, like before, if you were to std cout free store array, what would you see? You'd see the value stored in free store array, which is going to be the address of a dynamically allocated object. Therefore, when we see the delete operator in this instance, just like for the non-array objects, delete is being invoked on an address. So the address is that stored in free store array. We're not deleting a pointer. We're invoking the delete operator on an address. So let's go ahead and look at this a little bit more. So to dynamically allocate an object, we use the new operator followed by the type of object being dynamically allocated, and we store the address returned by the new operator in a pointer to an object of that type. So this is how it kind of looks. New ent is going to get us a free store object. So let me get some color here. That is going to create this object here. Now notice that this is an object of the primitive type. Its initial value is unknown. It's whatever's left over in the memory that is now being consumed for our integer object. Notice that this object on the free store has an address. Now we need to store that address somewhere, otherwise we'd have no way to access this object. So we go ahead and put that address in pint, which is a pointer to an integer object. Now notice here that address, that pint's value is the address of our dynamically allocated object. Recall here too that a pointer is an object in its own right, so it has an address as well. So just to be clear, here is our pointer object. It's storing the address of the free store object that was just had its memory allocated for it. And because we did not specify an initial value for that newly dynamically allocated object, its initial value is going to be undefined. Now let's say we wanted to go ahead and do something similar for an object of a different type, maybe a double. So again, it's just the new operator followed by the type of object who we'd like to have dynamically allocated on the free store. So in this case, it's new double. And that gives us back this free store object. And again, because this is an object of a primitive type, its initial value is going to be left undefined. Now again, notice here that it has an address and that we need now to store that address somewhere. Otherwise, we'd have no way to access this object. So that address is going to get placed into a pointer. And in this case, what is p double pointing to? Well, it's not pointing to an integer object. It's pointing to an object of type double. So p double is a pointer to a double object, and it is going to store the address of our newly dynamically allocated object. Now, anytime we would like to interact with, say, let me just highlight here to make the connection. I'll do this and let's do something other than, let's do purple. Anytime we'd like to interact with either a dynamically allocated integer object or a dynamically allocated double object, we're going to do so through their respective pointers. So if we wanted to access that dynamically allocated int, just get the right color here, I would just dereference my integer pointer, and that would get me this object over here. And I could go ahead and assign it, say, the value of 7. So at this point, that dynamically allocated object would take on the integer value of 7. Likewise, if I wanted to interact with that double object that we just dynamically allocated memory for, dereference the pointer storing its address. So that gets us from this address to that object, and we could say assign to it 3.14 or some other value. that's in both these instances we showed a write. We could also read the values stored in those objects by just writing, say, pint or p double. And in both cases, we have to dereference that address, and it would get us the value stored in the respective dynamically allocated objects. So what if we wanted to go ahead and start these dynamically allocated objects out with a well-defined value? Well, we simply go ahead and specify the value for which we'd like them to start out with. In the case of, say, an integer object, we might decide to zero initialize that. So initializing it with the zero value of the type, in this case, quite literally 0. To do that, we'd still have our new followed by the type of object that we're initializing on the free store, followed by the curly braces in the integer value to which we'd like that object initialized. And if we go ahead and look at that, we can see a brand new object whose memory is allocated on the free store, and its initial value now is defined to be 0. Likewise, for our double object, it's just, again, new double. And these braces, this brace notation here will not allow you to have any sort of narrowing conversion. So make sure that you're using a suitable initializer, in this case, 0.0. So this whole statement here, rectangled in red, is going to give us a double object on the free store whose initial value is or starting value is going to be 0.0. Okay, and we kind of referred to what's going on here, but we'll go ahead and go through it again. So how do we access a dynamically created object? To access an object that we've dynamically allocated space for, we're simply going to apply the dereference operator to the pointer that points to it. So if we go ahead and set up pint as a pointer pointing to an integer object residing on the free store, so we go ahead and create that object, store its address, and pint. You can see here, okay, newly allocated object. You can see its address here. And yep, the pointer got its address. By dereferencing pint, we are at this object now. We've gone out to its address, began interpreting it according to the base type, in this case, an integer. So we have that integer object back, and we can make an assignment to it, look into it, see what values residing there, etc. Now, the deallocation of dynamic memory. Remember, when we're dealing with dynamically allocated objects, it's going to be our responsibility to A, request them when they're needed, and then also return them when we're through with them. So to deallocate memory for an object allocated with new, we're going to provide the delete operator with that object's address. One important thing to note anytime we're dealing with dynamic memory is that every call to the new operator must be paired with a call to the delete. So if you have one new presenting somewhere in your program, you should have exactly one delete also within it. So to set this up, we create a new integer object on the free store. We go ahead and put its address in pint. So we have this nice object here. Pint is going to store its address to set up this relationship of pint pointing to that newly dynamically allocated object. Now, when we're through, we're going to pass the address of this object on the free store. So this one right here, we're going to pass its address to the delete operator. So we call delete followed by pint. Pint's value is that address. So right here. So when we write pint, delete pint, we're really writing delete followed by that long address there. And that's essentially going to communicate to the free store manager that we are returning the objects, returning the memory allocated at this address. One final thing, and we'll see the importance later on, is that we need to go ahead and assign our pointer to that object another value to communicate that it no longer points to anything. In that case, we simply assign the value of pint to be null pointer. And we'll see why this particular assignment here is extremely important, not in today's lesson, but in the subsequent lesson. So we went ahead with our, I guess, our first introduction to dynamically allocated objects. We're now going to go ahead and just decompose this a little further, see what's on the stack, what's on the free store, and then we'll go ahead and begin finishing some of the later videos that are going to comprise this lesson.